Good morning, friends. Let's continue our discussion about virtual threads. So, a server application in Java generally can handle concurrent user requests that are independent of each other. So, it will make more sense that if each of these requests, which are independent of each other, if it assigns one particular thread by dedicating a thread to each of that requests for its entire duration. Because this thread per request style is easy to understand, easy to program, and easy to scale and debug as well. Because it will be actually using the platform's unit of concurrency to represent the application's unit of concurrency. What we mean here is that if you got a server and each of the multiple clients which are connecting to that server and sending the requests, if the server assigns one thread for each request from each client, then it would be easier to have a very concurrent way of serving those requests by the server. So this is what and this style is like thread per request style is like the best way to handle all these type of concurrent requests from multiple clients. But there is a caveat here, right? Because as we know that if we, before Java 21, when we were relying on platform threads, each platform thread is generally a wrapper over a limited number of OS kernel threads. So that's why if we have got a huge number of client requests and we are assigning one platform thread for each request, then of course, there might be a situation that our system cannot handle so many number of threads because of the limitation of number of OS threads. That's why it will not be working and we might get some stack overflow error. However, the same problem is not evident when we are using virtual threads in Java 21, because as we have learned in our previous video that we can create a huge number of virtual threads which can be much more than the OS kernel threads available in the platform. So that's why we can actually use virtual threads for this thread per request style. So before we dive into further into the actual unit test code to understand this, let's try to understand Little's law first. So Little's law was a mathematical. It was given by a guy called as John Little, which states that a long-term average number L of customers. So this L of customers, this is dependent on the arrival rate of the customers, which is lambda, and if we multiply the average time that a customer spends in the system by W. So in other words, this W can be called as the latency. The latency, as we learned that this is the amount of time which a request needs to be served by the server. So here we are talking about the average time that a customer spends in the system. And arrival rate can be assigned as the number of concurrent requests that we are getting at the same time. And so this formula, L is equal to lambda multiplied by W, is actually given by Little's law, which can be used for our understanding about the latency, throughput, and concurrency in the current client-server applications. So let's actually take an example first to understand Little's law better. So as we mentioned that, suppose we have got a stationery in which we have got some customers which were coming to that stationery or to our custom store. So if we assume that customers arrive at our store at the rate of 10 per hour, so every hour we have got around 10 customers which are coming to our store and stay an average of say 0.5 hour. So each customer is staying at an average of 0.5 hour. It means that we can always say that the average number of customers in the store at any time to be 5 using the Little's law by using this L is equal to lambda 10. Lambda is 10 because the arrival rate is 10 per hour, and each customer is waiting there in the store for at least 0.5 hours. So if we multiply this, we get L is equal to 5. This is what Little's law states. We can extend the same concept of Little's law to define the scalability of server applications, and in which we can relate latency, which is the amount of time which is taken by the server to serve a request. Concurrency is that how many requests can be served by the server at the same time, and the throughput is the amount of requests which the server can handle per unit of time. So this is all being we can use the same formula here as given by the Little's law. If we go into at the actual example here, it would be easier to follow here. Suppose we have got a single threaded server, which means that once a request arrives from any of these clients, it will be serving that request in a serial order, like one by one. So if suppose client 1 has sent one request, the server will try to handle this client request first in the same thread. And if the other clients are also sending at the same time, they have to wait until this client 1 request is served first. So this is the single thread server. So suppose the latency of the server to serve one request is say 50 milliseconds. So after that, I mean, if you have got 2 requests, it would be, because it's serial, it will take say 100 milliseconds. For 3 requests, it will 50 multiplied by 3 is equal to 150 milliseconds. So it means that if we have got 20 requests from the clients to the server, to a single thread server, it will take around 1 second as per this formula. So we can say that the throughput of this single threaded server is 20 requests per second, because it's only able to serve 20 requests in 1 second. Now let's try to apply some concurrency on it. Suppose this server is not single thread server, but it can handle multiple requests at the same time. So if the server can serve 10 requests concurrently at the same time, so each, because each request takes like 50 milliseconds, but if we are executing all these 10 requests concurrently at the same time, the throughput would be 200 requests per second, right? Because we are able to execute 10 requests concurrently. Similarly, if the server can serve 100 requests concurrently, it means the throughput is going to increase by factor of 10, which is 2000 requests per second. So what we observe here is that even though the latency is still same, the latency for one request is still same as 50 milliseconds, we can still increase the throughput of our server by increasing the concurrency. What it means is that if we can assign one thread per request style, it means that we can have a huge number of concurrency in our system, which will definitely improve the throughput without the need to improve the latency of the system. Latency is still 50 milliseconds. If we keep on increasing the concurrency of our server, the throughput is going to be increased in the same factor. So this is what we want to explain by using of virtual threads. Because by using of virtual threads, we can actually achieve this thread per request style. We can execute lot of client requests concurrently, which will definitely increase the throughput. One point to note here is that virtual threads cannot improve the latency. For latency, we have to see that how the server can improve the latency by optimizing our methods or the data structure that we are using. What we are talking about is that using virtual threads, we can definitely improve the concurrency, which will result in increasing the throughput of our system, of our server application. Let's understand the same concepts using some unit tests. So I created a unit test here. So here, let me go through this unit test. So here I'm going to use large number of virtual threads. So here I can use executors.new virtual thread per task executor. So let's actually, before we go through the unit test case, let's talk about the thread pools that we have in Java. So this is how a typical executor service works like. That we have got a task submitter, which will submit some runnable tasks or callable tasks to this task queue. Inside the executor service, there is a queue which will be receiving all these tasks from various threads to be run by the thread pools. So whenever we create a executor service by using a cached thread pool or a fixed thread pool, in that case, we have got some certain number of threads which are already created in advance. For example, for the cached thread pool, it will be the number of threads which will be there in the thread pool, which will be created, would be equal to the number of virtual cores that we have in our system. Similarly, for the fixed thread pools, we can define a specific number, that how many number of threads we want to create in our thread pool. And we have got a blocking queue or unblocking queue. It depends on what type of implementation that we're using. We can customize it as well. But the basic idea is that when the tasks are submitted, it will go to the task queue, and whatever threads are available in the pool, they will keep on consuming this task and then keep on executing it. So the task, if the number of tasks are more than the number of threads in the thread pool, those tasks has to wait in the queue until one thread is available or done with a task, and then it can consume that task to execute it. So this is how a typical executor service works. So here in Java 21, we have got a new type of virtual thread per task executor pool created, which will only create virtual threads instead of using the platform threads. as we'll see in the next two examples. So here we are using this factory method that we are using executors dot new virtual thread per task executor. As we have learned that this will create a virtual thread per task. Now we are having a in stream of range from 0 to say 100,000. So this is 100,000, and time to sleep is 1 second. So if I go back again, so here we are actually having a stream of range from 0 to 100,000, and for each of them, it would be submitted to this executor that we have created, which is executor of virtual threads. And we'll submit this task. The task is doing nothing, but it is just going to wait for some time. And here we have defined it as like around 1 second. And here we have also created a map, a concurrent map, which will just use the key as the current thread name, and it will keep on incrementing if the same thread has been used to execute this task. If it is like first time, it's 1. Otherwise, it will merge and it will increment it by 1. So if the same thread is being used again. So this is our main our submit task. And finally, because we are using try with resources, it will close automatically when this try block finishes. And then we will check the total time elapsed, that how much time it took to like completely done by this executor pool to execute this test. And then finally, we will display some stats here. This stats would be the total latency, where we will give the time elapsed, and then the throughput, which is how many requests per milliseconds that we have done, and which is like the time elapsed, which is time elapsed is milliseconds, and the word types maximum, as we know, is 100,000. And then the number of threads used, because we are actually using that how many number of threads that we are using in this key map value. And finally, we will print out the whole map just to like see that how many, what is the value for each thread. If the same thread has been called multiple times from the pool, as we have learned here, that the same thread can be used multiple times for if the tasks are increasing, the same thread would be returned to the pool and then it will consume the next task. So the idea is that we actually have to like check that how many times a particular thread was used to execute this task, and we'll keep on incrementing. So we have got this display stats as well. So let's run this and see that what is the time taken by this virtual thread pool to execute this task. So if I run this, let me click on run button. So this test is completed, and here we have got this total latency is only 6092 milliseconds. This can be further improved if we have some JVM warm-up, but still it's like quite impressive. It only takes around 6 seconds to serve 100,000 of requests. And the most astonishing figure is that it's only using only one thread, because the task is so simple. It's only like waiting for say 1 second, but still it is like so optimized that it's only using one thread to achieve this type of latency and this type of throughput. And as we see that our threads count cache, it is using the same thread, and it is incrementing, and that's why our 100,000 tasks are done by the same thread. So let me copy this, and then we can use it for comparison with the platform thread pools. So we have got these figures, which is quite impressive as such, and number of threads are only used as 1. Now let's run the large number of cached platform threads. So when we use cached thread pool, as we mentioned that the thread pools will be having when we create it for the first time, it will be having the number of virtual cores that we have. The same number of threads would be there in this cached thread pool. And every time when we have got a new request, with the request coming, and all the threads are already being used for the new task, it will create a new thread immediately. So it will keep on incrementing the thread as it will try to like not have any waiting time for any task in the queue. So this is the approach for the cached thread pool. Every time we have got a task and we don't have any thread in the pool, it will create a new thread. And there is some other like statistics that it will wait for 60 seconds. If there is no task in the queue and a new thread has been created, it will just make that thread dead, and it will remove that thread from the pool. So this is what the cached thread pool is. So again, let's run this and see that how it goes. Large number of this. I will just pause it for now. Now, as you see here, this is for the cached platform thread. So total latency is 15 seconds around. Compared with the virtual threads, it was 6 seconds. And now for cache thread pool, it's 15 seconds. Throughput has decreased from 16 requests per millisecond to 6 requests per millisecond. And see the number of threads used is 15,387. And if you look at the thread counts cache, we can see that, say, for example, one cache thread has been used 10 times, sometimes it has used 9 times. So it will, as mentioned, that it will try to just create new threads on demand as we have got incrementing number of tasks in the task queue. So this is the behavior, and we can see that the performance is like dismal as compared to the virtual threads. And also, as we have seen that, although my system can handle 15,387 threads, but there is always a limitation. If it goes to like millions of requests, millions of threads, I mean, definitely there would be a limit, upper limit, and the program may crash if we have got a huge number of threads there. Now let me copy this as well. I will copy this, and also, like, just for the comparison, I will use it here. Okay, so number of threads. Now let's go back to the fixed pool threads. As we mentioned that we can also, instead of creating a cached version, we can also create a fixed thread pool of, say, 200 threads. So it means that all the 200 threads would be used here in this pool. And if there are 200 tasks, each of the 200 tasks has been like executed by the current 200 size of thread pool. For the 200 first task and the other task, they have to wait until one thread is available in the pool because it has got a fixed size. So there is nothing like a cached thread pool where a new thread would be created on demand based on the task queue. The other task has to wait there. So this would be having a very dismal performance, as we know. But this will actually help us to just one thing is that our program will never crash because we are actually well under the limit of only like 200 platform threads that we are using. If I run this, you can see that I have marked this as disabled because if I run it, it will take a lot of time. So what I've done is that instead of waiting for, say, 1 second, just wait for 1 millisecond. Okay, so let me wait for 1 millisecond, otherwise it will not even work. I have to wait for a very long time. And let me click on run. Okay, so as seen from the output, because our latency has been decreased permanently by from 1 second to by a factor of 1,000, it's just like 1 milliseconds. Of course, the latency and throughput would be much better. But and you can also see that number of threads used is like 200. But if I just again change it back and just run this, I don't think it will finish immediately. It will just take a lot of time. I just click on run. It will keep on running for a very, very long time. So yeah, as you can see that it is just going to run. Okay, so if I wait there for, I think, maybe in minutes or I don't know, even hours it will take to finish this. So anyway, I will terminate this because it's not going to work. So this is what we want to discuss, that if you're using the fixed thread pool or the cached thread pool, of course, using the cached thread pool, it would be it's possible to, like, if we have got a certain number of threads which are created, which are well under the limit. So in our case, we saw that it's even for 15,387 threads were created, which are still supported by my system. But if it goes into like 100,000 number of threads or something like that, definitely it's going to fail because we have got very limited number of OS kernel threads as a wrapper over the platform threads which are created by the cached thread pool. So guys, this was all about the limitation of current server applications with pre-Java 21, where we try to use cached platform threads and fixed thread pool threads, and we found that it's a limitation that we cannot create a thread per request style. But using Java 21 virtual threads, definitely we can create lot of number of virtual threads, and the throughput can be increased tremendously. In the next video, we'll proceed our discussion about same virtual threads. But before that, we'll try to understand more about blocking, non-blocking, and asynchronous server. And we'll extend the same concept that we learned today regarding the Little's law and the thread per request style. And we'll extend that the same phenomena by using multiple clients and server requests, and see that how the virtual threads can improve the throughput. So see you all in the next video.